DeepQ networks proved that reinforcement learning algorithms could successfully process high-dimensional sensory inputs, like unparsed screen pixels, and map them to successful policies. But that success relied heavily on the constraints of the virtual environments it was tested in. The model was only required to choose from a tiny menu of binary outputs. It was essentially deciding whether a specific button was pressed or unpressed at any given frame. Physical robotics cannot operate on binary outputs. The real world demands continuous, real-valued actions. Moving a limb requires applying varying amounts of continuous torque to multiple actuated joints simultaneously, maintaining fluid momentum over time. Mastering the logic of an Atari game is a discrete puzzle. It offers no proof that an algorithm can navigate the high-dimensional, continuous reality of physical space. The mathematical bottleneck lies in how standard Q learning chooses its actions, finding the Grady policy by calculating the argmax of the Q value. In discrete spaces, this is an instantaneous lookup. The system checks the expected reward of the 5 or 6 possible button presses and simply selects the highest number. Look at this continuous Q value landscape. Between any 2 points, there are infinite possible torque values. An exact lookup is mathematically impossible. Finding the exact maximum Q value here requires running a slow, iterative optimization loop at every single time step. Attempting to bypass this by cutting the continuous curve into small, rigid settings triggers the curse of dimensionality. If you discretize a 7-degree of freedom robotic arm to just 3 coarse settings per joint, you immediately create an explosive action space of over 2,000 distinct choices per frame. Engineers cannot force physical reality to become discrete. To control physical systems, the argmax optimization step has to be entirely abandoned. To bypass the optimization trap, researchers moved away from standard Q learning and adopted an off-policy actor-critic architecture based on the deterministic policy gradient. This setup introduces an actor network. Instead of scanning a value landscape, it maps the state directly to one continuous action vector. A critic network then acts as the evaluator, taking the state and action to output a single value grading the action's effectiveness. The system learns by applying the chain rule. It takes the gradient of the critic with respect to the action and multiplies it by the gradient of the actor with respect to its own parameters. The critic directly informs the actor exactly which direction to adjust its parameters to achieve a higher score on the next attempt. By splitting the workload into an actor that guesses the specific output and a critic that grades it, the intractable argmax search is eliminated completely. While the underlying math of the deterministic policy gradient was sound, replacing simple linear approximators with deep neural networks in this specific setup historically led to catastrophic system failure. The deep network would fail to converge, producing wild, erratic fluctuations in its value estimations. The mechanical flaw is in the training loop. The exact network being updated is simultaneously used to calculate its own target value. This creates a recursive feedback loop. As the network adjusts its parameters to hit the target moves in response. The network ends up chasing its own tail. Any incremental progress made on a problem is immediately destroyed by the subsequent learning updates.
The barrier preventing continuous deep reinforcement learning was not the capacity of the neural networks, but an optimization architecture that inherently bred instability. The authors of Deep Deterministic Policy Gradients, or DDPG, solved this instability by directly importing the stabilization techniques that made DQN successful. First, they broke the assumption that incoming data is independently distributed by adding an experience replay buffer. By sampling randomized mini-batches from this cache, the algorithm learns from a broad set of uncorrelated historical memories, rather than the highly correlated immediate present. Second, they duplicated the architecture entirely, creating separate target networks for both the actor and the critic. Instead of abruptly hard-copying the weights from the main network to the target network periodically, DDPG implements continuous soft updates. Through these soft updates, the target networks only absorb 0.1% of the learned network's weight changes at every single step. By forcing the target values to adapt at a glacial pace, DDPG converts the highly volatile reinforcement learning loop into a stable supervised learning problem. Scaling this to robotics required addressing the physical properties of the data. Physical states utilize vastly different units, pitting joint angles against rotational velocities. To prevent the network from collapsing under these varying scales, the input dimensions are run through batch normalization. Whitening the input data ensured the researchers did not have to manually tune the network's hyperparameters for every new physical environment. The final conceptual hurdle was exploration. Because the actor policy is deterministic, it will map a specific state to the exact same action every time, effectively preventing the AI from discovering new solutions. DDPG forces exploration by injecting an Ornstein-Uhlenbeck noise process directly into the output action. This specific noise process is temporally correlated. It generates smooth variations that respect the physical momentum of a moving object, rather than introducing chaotic, random jitter that would snap a robotic joint. With batch normalization unifying the data stream and temporally correlated noise safely driving exploration, the architecture was equipped to handle high-dimensional physics simulations. Testing this model-free algorithm resulted in robust solutions for over 20 different simulated physics tasks. It accomplished this using the exact same network structure and hyperparameters for every single task, from balancing a monoped to navigating a driving simulator. By utilizing action repeats, DDPG learned these continuous physical control policies end-to-end, inferring velocity by stacking raw, unprocessed pixels. The study measured these results against a baseline set by an advanced planning algorithm called ILQG. The ILQG planner operates with an immense advantage. It has omniscient, full-state access to the underlying simulated dynamics and mathematical derivatives of the physical environment. Despite operating completely blind to the underlying physics model, the DDPG algorithm consistently discovered policies that were highly competitive with, and in several instances superior to, the omniscient planner. Deep deterministic policy gradients proved that the mathematical chaos of continuous action spaces could be mastered, as long as the underlying optimization architecture was finally forced to stabilize.